mass is the big N, meaning it's sitting on the spring. Unsprung is the little m. This you want to minimize. You want to minimize that too, the sprung mass, but it's the ratio between the two that kind of drives it. You want this to be much, much smaller than that. So calculate the sprung corner weight m, then calculate the k wheel from omega equals square root of k over m. Then calculate your motion ratio from suspension geometry. So that would be like the sine theta and the a's and the b's. Yeah, it would be like that with sine thetas. And then you can get your spring rate, calculate k spring from k wheel equals motion ratio squared times k spring. Great question.
And also for the M, do you divide by 4 because it's 4 wheels, or you just?
Yeah, and so that's what corner weight actually means.
Okay.
Yeah. So the full picture would be, let's see, here's your car, wheel, 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 wheel. You have a center of gravity location in the top view. That'll give you, let's say your total mass is 300, and let's say you have a, let me make the numbers easy, 40% front, 60% rear. That means 20% is on that tire. So 20% of 300 is 60 pounds.
Yeah.
But then you know the tire, you have to, so let's see. 20% times 300 pounds equals 60 pounds. That's the weight of the contact patch. But we want to pull out the unstrung mass because this formula applies just to those two, not to those two.
How will you know the unstrung mass?
Yep. So you would take usually it's mostly the tire, the rim, and the hub.
Oh, so you have to weigh them before you.
Yes, we have to. So I would take that tire, that rim, anything that is connected. Let's see if I can get a good picture. That's a pretty good picture. So the unsprung mass would be the tire, the rim, the hub, the brake disc, the upright here, and then typically what you do is take half of the A-arm weight and you proportionalize the spring and the shock weight. Or you could just take half of those two. You just wanted the ballpark. So we have 60 pounds. That's at the contact patch. And we subtract the unsprung weight. And I'm going to guess that's like 10 pounds. And we have 50. So that would be corner weight.
So usually you just have 2 types of springs, 2 for the front and 2 for the back?
Yes, yes.
Unless you have 1 brake on 1 tire, if you have a spool.
No, the spool would the spool would still have the same spring on left and right. With the place
I mean, when you calculate the weight of the tire, you only have the brake on
I
one
see.
side.
If one side is a little heavier than the other, then you could have a different spring. But usually those differences are so small.
No, okay.
Yeah, but you're right. It's possible. And circle track cars, they actually have their CG biased to the left side of the car, and they do have different springs in all 4 corners.
But we're not there. Good symmetry, right?
Yeah, you can assume symmetry. Yeah. Yeah, great question. So that's the spring rate calculation.
That's good.
Okay. So the key concepts here are motion ratio. Let me get a sense, how many are comfortable with that formula? The squared in particular? Pretty good? Yeah. So I don't need to derive more. There's another subtlety to the motion ratio, and that's this idea of rising rate. So, what should I write this? Here's my car. Here's my simple suspension. Oh, sure, I'll put a vulture down there. No, that's not. Okay. My spring point, the question is, where do I put my spring? And so we talked about motion ratio, didn't say what you want. Motion ratio, the goal is to maximize it, almost always. The reason is that if the motion ratio is low, then your forces get multiplied. So if I put my spring like right in the middle, then a 10-pound force here gets turned into a 20-pound force at the spring. And that means this mount has to be twice as strong as it would be if you put the spring here. And this arm, it's really bad for this arm. So compare this design. If you do this, now you're putting a large force right in the middle of the suspension arm. Lots of bending. And that means that arm is going to break there, or you're going to have to reinforce it by making it into that shape. Now it's heavier. And more expensive because you had to do that. Compare that with this design, where I put the spring right out far. Now this 10-pound force goes to like 11 pounds in the spring. The arm is in almost no bending because you got the force way at the end. And this spring perch, if you can get your frame designed so that there's a natural perch here, then a natural strong point, then that force is lower as well. It doesn't have to take the load. So we always try to get our, not always, in road racing and street cars, we always try to get the spring as far out as possible. Trophy trucks are different. Because you've seen those rear suspensions, we'll talk about those. And I think this is a special case when you've got, they got 22 inches of wheel travel. My guess is the issue is they can't buy shocks that are 22 inches travel. Or if they can, that those kind of shock velocities are so fast that they might get foaming or something like that. So they actually have motion ratio about 0.5, which is pretty low. But I think at Baja, I don't think we're in that. We are not doing their kind of speeds. We're not hitting bumps at the speeds that they're hitting them. And we don't have 22 inches of wheel travel. So you still want to get the spring outboard. Let's see, so the guidelines are for front suspension, it's tough to get a real high motion ratio because just packaging. The wheel has to turn around this thing, right? And usually you can't get it that far out on a front suspension. You'll get it to about there, and then it starts to run into things. So front suspension, good motion ratio would be like 0.7 to 0.8. Bad would be 0.5. In a rear suspension, it's different because, let's see, let's take a rear suspension, you can actually actuate the spring right off of the upright. Because that wheel is not turning, and so you can like put a little perch there, put the spring right there. So rear suspension, you can usually get 0.9. Okay, so that gives you some ideas about the targets. But there's another cool thing you can do with motion ratio. And it has to do with, does it stay constant or not as you move the wheel? So you might imagine that the goal of the wheel rate is to stay pretty low so it can be supple over bumps. But at some point you are going to run out of wheel travel. You're going to hit a bump that's so big and you're hitting it so fast that the wheel goes all the way through its travel, and then wham! The shock runs out of travel and it all goes into your car. You'd like that to not happen all at once. You'd like it to be like, give you more resistance as you go higher into bump. So that's called a rising rate. And there's a couple ways to do it. One of them is, let's see. So let's say this is the ride height configuration. And let's say this, let me just do a stick model. Oh gosh, we've been going an hour and a half. You guys dead? How about we take 5 minutes? Sorry. Let's take a 5-minute break. Stand up. Become awake.
Oh, you're everyone.
If you lose the coefficient of friction,
Thank you.
They always told me you have to once in the break when you go to the AP Super corner. To have away from
It's weird.
the important thing is always like how
Like you can see like the top of my head. Yes, you may. There we go. That's way better.
Okay, well, there's what we're fighting is the idea of friction circle. Remember the friction
Yeah.
circle?
Softball.
Yeah. So
Hey,
if
I
you're
miss
braking,
you.
then you're using some of your tractive force for braking.
Are you on the
And that
chassis
means you
team?
have less available to you.
Chassis.
Let's see. Here's braking. Here's braking in the corner.
I'm gonna prepare like a.
That's why you normally the brake graphs is you got those friction for the first part of the brake and
Pretty
then
good.
you decrease the
Yeah,
brake,
yeah.
and with your,
Yes, you turn the steering wheel more as you come off the brake. Yeah.
That's why you can't just keep the brake all the time and quite all the time.
Right, you can't do both, because that would be, you can't do both full cornering and full braking at that point.
Also, we're talking about the suspension of the truck that has the point under the ground here, and so that's really bad because when you brake, the ground
Stretches a lot, yeah.
all your system.
Okay.
Let's see.
Do you want to wear a shirt?
Actually, no, this isn't like serious.
Oh,
We're gonna make like
oh,
a team
have
Yeah, you cross the, you share.
have an anti-roll bar or an anti-pitch bar.
It's like just
I didn't
connected to
see you in
suspension.
here.
Oh,
Yeah. Snuck in, I snuck in the back. Gross.
How do you spell that?
Do you guys know too many
Oh, hydraulic.
engineers
Oh,
that are like
yes.
software?
You can connect from left to the.
No, I mean, like, I know some.
Cross it,
Because I'm
and then
not
it reduce the.
Oh.
Hey, you know some too.
Well, you have.
Okay, yeah, yeah.
Oh,
You know,
Like,
they feel that
friends
from the
and
one
stuff.
that like here.
Oh, I haven't followed it.
I don't follow.
No, I mean, not that closely.
It's like
That can do.
it's a system that connects the suspension
Ah.
that maintains the car flat, so they are like not having more loads at the same time. So
Yes.
when you brake,
Yeah.
you increase the degree of the flat of the oil and things like that.
Right.
So they connect the
Yeah.
Vice president of FAE. Oh.
Like
we need a president.
It was research
Yeah.
and it was like,
Okay.
traffic trying to be
But,
a improvement.
Ah.
Yeah, so we should like some of the other people to, if they're
Yeah,
interested in
yeah.
I think the front left here
to build us.
rear right.
Yeah.
And reduce quite a lot the amount of gauge.
Yeah.
Oh.
My sense, I don't know for sure, but
They're
my sense is
pecan
driving trucks don't need to
caramel
brake a lot.
patties.
That they are mostly going over rough terrain and.
Oh, I already had one. That's
It's
just
just pretty weird because all the
Thank you.
cars is
Great.
asphalt.
Yeah,
So
yeah,
it's
yeah, off-road is a different game, yeah.
Well, I think you actually, if you're a driver, you would like to have the car to roll over. I was like,
That was me
that's
yesterday.
it. Like, it's the worst car from Renault. They
Oh.
got a cheaper version of that.
Uh-huh.
And they come out for the trophy, race with this kind of car. And I tried one time in a circuit. And you
I was
would
reading
turn
a
and
blog and it was
the-
like, you should be
the-
hungry like
flip
75%
over
of
with
the time.
suspension.
Why?
Yeah, yeah.
Because if you're
Like,
always
turn up all
eating
the
to fill
color
your
that's
hunger,
very
you're
bold.
never
Yeah.
actually letting
So,
your body
actually,
go into like a
for
hunger
cars,
mode where it's actually digesting all of the fats.
Yeah.
So it's good
That's good, yeah.
Uh-huh.
because then you're digesting.
I guess this would be too complicated.
For what research, it's just.
Apparently.
That's
It's
it.
on a blog.
Well-
So that's probably not very reliable, but
You know what?
I read that.
And you copy that one day on Tuesday.
Yeah.
Oh, I know, she's gonna be,
Maybe.
oh no,
That's
today,
fine.
today she's
Oh, throw
gonna
that.
have a bath when we get home and then her nails get clipped too.
And that's all gonna happen so we can get to this.
You're such a beggar. Yeah, I mean, she's not coming.
She's not?
No.
Oh, Charlie doesn't wanna go now.
Huh? No, she's not coming.
Oh.
It's just
You just
easier
don't
for
like talking
me.
about Molly.
It's just easier for me, plus there's like a family fire and it's gonna be dark.
Yeah, that might be
It's
really
just
hard.
better just not to have a little puppy.
Yeah, it's-
Were you not bringing her to?
Fiesta Island today.
Oh.
Yeah.
She wants to go on an adventure.
No, she doesn't. She'll just want to eat all the
No,
s'mores.
no, she does not.
So, no.
She gotta go to class.
Yeah.
Didn't they should have such a low growl?
I know. It's not yappy. Layla.
That's what I like the whole,
Oh,
like, individual, like,
Hi.
what's up? All the way around the room.
So the cosine of cabin, does it also account for like, you know, how you talk about, like, maybe just bring at an angle. This. It would become like a 90 degree.
Oh.
Ah, yeah, that's where.
Watch out, the dog will lose. His eyes.
اللي بلبسها قلب
Just you picking the instant
لا كيف
motion ratio.
لا لا
At a moment in
لا
time. And then you also look at how does that motion change as you go through travel. That's more helpful.
عشان شي يعطيك احلى لحظه شي.
Wow, that's it.
Okay,
Nice.
let's get started. We can finish what we're talking about here.
تذكرت يقولوا لي حرف انا تذكرت.
So we would like to have the motion ratio increase as the wheel goes further in the bump. That will keep us from bottoming the suspension out. And there's a simple geometric way to achieve this. So let's say the blue is the car at ride height, normal ride height. And the black is the wheel with full bump. That's the max travel.
I just, it was on the floor.
If you
right
take
there.
a perpendicular
I didn't know whose it was. I just, it's felt so many steps.
from that
Sorry.
line,
It was on the floor.
Yeah.
and if you mount the suspension anywhere, the upper point of the strock, anywhere along that line, then initially the spring has an angle, so the motion ratio is decreased a little, and as you go into bump, it approaches more and more 90 degrees, and that spring is actuated more directly. Pretty simple.
Nothing better.
That's better, yeah. It's not dramatic, like it might go from 0.5 to, might go from 0.7 to 0.75, but when you square it, that's a big difference. The other way to get a rising rate wheel is to use a nonlinear spring. So this is a normal spring that you're familiar with. They can also coil springs with a narrow spacing at one end and then a wide spacing at the other. The idea here is that as you compress this, at some point, this set of coils will stack together, solid. And once this becomes solid, now you just have that spring. Since it's shorter, it's stiffer. And then the next level is, why don't we do this progressively? So that first that one compresses solid, then 3, then 4, then 5. So this one gets stiffer as you go. So those springs are nifty. I think they're used in motocross a lot, but of course they're more expensive. So that's the wheel rate. Let's see. I think I'll work directly with the suspension teams to do double A-arm analysis, because that's kind of involved and detailed. This one affects everyone though. This is the idea of bump steer. Because both the chassis team and the suspension team need to know about this. So we want to have the wheels not turned as they go up. We want them to stay the same toe or to be able to control that toe very precisely. And geometrically, the way you achieve it is, like, let's say you have a double A-arm suspension, front suspension. So we have a tie rod, and this is going to make the wheels turn. First, you find the instant center of your upper and lower A-arms here. If your tie rod points at the same location, that's the first step to getting almost no bump steer. The second step is getting its length to be proportional to these. So the way, this one is set in slightly, and there's reasons for doing that related to Ackerman. But if I took the length from there to there, and I just move that over, if I get the length correct by that, and I get pointed at the instant center, then you should have very little bump steer. There's also what's called roll steer, and this applies to solid axle vehicles. So if I'm driving and I got a solid axle behind me, as the car rolls, I would like those rear wheels to not toe out. I would like them to toe in very gently. And that's achieved by how you design the rear suspension. Now, these kinematics can get pretty complicated, and so there are dedicated programs out there. Some are free, and they aren't bad. The free ones aren't bad. Typically, they're $300 to $600. And you give them all your geometry, XYZ points, spring, everything. And you can make the car go up and down, and it will tell you things like, what's the camber of the outside wheel? What's the roll center height? How much did the toe change? It can also tell you, did the wheel go left and right? That's called scrub. You don't want it to do that. These are all the XYZ points. There's one of these programs that's online, actually. Let's see, where's that link? Oh, yeah, this one. racing aspirations. This is only a 2D program, but it gives you a feel for what it can do. And I have one of the 3D ones. So here's a little double arm suspension, inches, bigger. This won't tell me toe because it's only 2 dimensions. But I can pull that vehicle up and down and look how the camera changes. And it will tell me the camera here. If I log in, I can get some more data. And you can roll the car. And you can also move the suspension points. Let's see, how do I do that with that? So I can relocate. Oh, actually, this is instructive. When you have, so the difference between parallel and short arm is the short long arm suspension, when the upper arm is shorter, it tends to give you better roll center control as the vehicle is rolled. I can't show you that because I have to log in for it. Let's see, and then what else can we do? Oh, the longer the arms, the better, in general. So this suspension will have less dramatic movements of the wheels for a given amount of chassis movement or a roll. So that's fun to play with for kind of your initial trials. I would probably work out most of my issues in 2 dimensions actually before I went to 3 dimensions because just more data to keep track of. So I can work with it. I've done a lot of this kind of suspension tuning. That's some of the cool tricks. You can also configure SolidWorks or Creo to give you this data. It just requires a lot of what do they call it? Formulas that you can put, and it can spit those things out for you. Yep.
Do you recall the name of the 3D free program that you were using?
Yeah.
Just so we can pull that up at some point.
Why don't you email me and I'll send it to you. I forgot. Okay. Let's see. While we talk about spring rates, this is a good time to talk about ride. So in terms of these frequencies of 1 hertz, there's a little distinction that's made on the front frequency versus the rear frequency. And the idea is this. So let's take this car. So as this car goes along, the front wheels are going to hit this bump. And then the front is going to start responding to that bump. And the front's going to kind of go like that. If you want to have the driver as comfortable as possible, there's a trick you can do. If you make the front frequency and the rear frequency the same, then going over a bump, the driver will feel the front go up, and then they'll go over the bump and they'll feel the rear go up, and they'll go through that process. But if you make the front frequency softer than the rear, so the front might be 0.9 hertz and the rear is 1.1 hertz, then instead of that experience, the driver feels, hits the bump, the front starts to rise, but it's slower. It doesn't rise as quickly. And then the rear hits the bump, and it goes like that, and then the whole car just kind of goes flat. So it's the difference between porpoising. So if you porpoise, then the front goes up, the rear goes up, and you feel this. And if you make the rear frequency stiffer, the front starts to go slow. The rear, being stiffer, responds faster, so it's level, and then it just comes down level. So that's the front-rear ratio. So front might be 0.9 hertz. I'm just making these numbers up. rear 1.1 hertz. There's ways, it depends on your wheelbase and things like that, but there's ways to calculate how to make that happy. Now that is for comfort, but a comfortable driver is a faster driver, so that's an argument for it. The Formula One and those kind of racers, they'll do the spring rates just whatever they need for the aero. And the drivers, that's tough. You know, but with Baja, we got such big bumps. I think this is probably in your favor. Okay. Well, we covered quite a lot. Why don't we end with some fun stuff looking at pictures? Yeah, so here's a trophy truck. 22 inches, close to 20 inches. Parallel arm, double A-arm suspension here. You can see very long arms. If you want a lot of wheel travel, you just have to have long arms because your wheel travel is at some point limited by how long the arms are. There's no way around it. And similarly for the back, this long trailing arm, that pivot, that pickup point for that trailing arm is like under the driver's seat. And that way this, this rear wheel does not go through a big angle change as it goes through its huge travel. It has a more consistent anti-squat and precession or recession. Solid axle rear. This is an older style suspension. It's called a twin I-beam. And each wheel, instead of on an A-arm, has a single arm pivoted on the opposite side of the car. And the big disadvantage of this one is that massive camber change, you know, but it's a very tough suspension. There's a trophy truck hitting a bump. Yeah, these, and there it is in the opposite situation. You can see very long arms. They've got them almost connected together here. So if you want to maximize wheel travel, you need long arms, both on the front and rear, no matter how you do it. So some things to look at. That's an independent rear suspension truck. So this is called articulation, when each wheel is doing something different. Here it is going over some rocks. So one of the, I mean, we talked a lot about handling here, roll centers, camber angles. When you're talking off-road, fundamentally you're talking, does it have a lot of wheel travel and is the suspension supple? And if it doesn't have those things, roll centers don't matter. So let's see, that was one good one. I have a few others to show.
Suspension,
This is a radio-controlled trophy truck. It's a tiny one, but he's put a GoPro in the truck, and it has a great view of the rear suspension coming up here. So this is classic trophy truck rear suspension. Single trailing arms that are real long with a pivot point right under the driver. Then there's another link. This is like an A link. But this can either be two joints or one joint, it doesn't really matter. The roll center of this thing is defined by this point, or the intersection of the two. This gives it the lateral stability. You can imagine without that arm, then a suspension can move laterally. So since it's giving lateral stability, that's why it's good for roll. But you can see how this one moves and rolls. Even though it's a dependent suspension, it is capable of single wheel movement. You can also see the spring is actuating in the middle of the arm. And this is how all trophy trucks are. And that means they need to have this extra thick suspension arm so it's more unsprung weight. But there must be a reason they do it. I don't know what it is. We need to ask them. I think it's because what I said before, just physical limitations of shocks. Okay. Let's see, some other details on trucks. Here's a good example of a frame design. So we talked about frame triangulation with the frame team. If you have triangles everywhere and you feed your loads into the joints of the triangle, like that spring is coming up very close to this joint, and then it's all triangles as you go backwards. That's now a truss, and trusses are 10, 100 times stronger and stiffer than frames are. In other words, if I didn't have that diagonal, this diagonal, and so on, then those tubes go into bending, and bending breaks stuff so much easier than tension does. The rear springs tend to actuate in trophy trucks to this kind of weird member here, and I don't know why they don't get it to go to a point. I would rather go to that point or this point, but it maybe it just doesn't package. You can see how massively long that arm that is. Here's double A arm for a front suspension, very close together to maximize that arm length. You can see that the tie rod for the steering is pointing in the same direction as the ensign center, parallel. And they've got the links. If you draw a line through that point to there, that's intersecting it. And same thing there. That's for bump steer. Again, they're putting their spring far inboard. That's a motion ratio of 0.5. So I'd like to know why they don't put it out there. That's where I was always taught and makes sense to put it, but there must be reasons why when you've got that much travel, maybe you need to put it inboard. Another front suspension. The lower ball joint, you can see they're trying to tuck inside